So today I'm going to talk about the Bomba Polska, the Polish Bomba, of which you could consider the Turing-Welchman bomb, which you can see as my background, as a descendant. So I'm just translating that to English for you. Now this device, we don't really know what it looks like. It was created just before the outbreak of World War II. And this is a fairly rough engineering diagram that was created from that era. There was a film made in 1973 called Secret Enigma, based on a book of the same name by one Stanisław Strumpf-Wojtkiewicz. And this book and film tell the story of the Polish breaking of Enigma prior to World War II. And this shot here, this screenshot here, shows a number of Bombe working away. It's not particularly guaranteed to be accurate. There's a couple of Enigma machines you can see in the front here, which look nothing like Enigmas. So there's no reason to suppose that this is particularly accurate either. And this is a second shot closer up. The chaps in the uniforms are Poles and French people, of a French person, Gustave Bertrand. The chaps in the suits and the naval uniforms are British. But they all speak fluent Polish in this movie, I would add. And I would also add that Adolf Hitler appears in this movie from time to time, and he mysteriously speaks fluent Polish too. This is a modern engineering diagram created, which was supplied to me by a gentleman called Marek Grajek, who will be giving a talk next month about the foundation of the Bureau Szyfrów, the Polish Cipher Bureau. It's in our events calendar if you want to take a look and join us again then. The documentation dates back from that era, the main documentation. And as you can see, it's a little bit scratchy. And what's interesting about this documentation is that Polish has a lot of accented characters, a lot of characters with diacritics. And this was being typed on almost certainly a French typewriter. So you can see, for example, this second word here, więcej. There's a hook being added to the E because that's a Polish diacritic that obviously you don't find on a French typewriter. And here we have odgrywałoby, and the L has a diacritic on it. Again, not one you find on a French typewriter. I have created a simulation of the Bomba, which I have sitting on a desk to my left, and I'll be running it. Well, I'll be showing you a video of it running and also doing some explaining around what it does in due course. But first of all, and I know a lot of you know about Enigma already, but there may be some of you here who are not so familiar with the operation of Enigma. So this is a brief introduction into Enigma and the various breaking methods that were developed primarily by Polish engineer mathematicians. So let's start off with a quick definition of what is an Enigma machine. And the answer is, according to the next page, when I'm obliged to make this copyright statement from Paul Roivers of the Netherlands and Frode Weilwood of Norway. This is a family tree of all possible Enigma machines. And as you can see, there's some 20, 25 of them. And this is an example that you don't see very many of. It's a printing Enigma. This is a numbers only Enigma, which was probably used for encrypting and decrypting weather forecasts, which are broadcast as numbered texts. This is a standard 3-rotor Enigma, which is the one which we'll be concentrating on in due course. And this is a 4-rotor Enigma. The difference between this one and the previous one I showed you is there's no plug board on the front down here there's a plug board. On this 4-rotor version there is no plug board, but there's an extra wheel on the left-hand side. This is a rather special Enigma of which only 2 are known to exist. This one is currently on display at the Instytut Józefa Piłsudskiego w Londynie, or if you prefer that in English, the Joseph Pilsudski Institute of Hammersmith in London. It's somewhat unusual. Its design is somewhat unusual compared with other Enigma systems. The keyboard, instead of being standard German Kurzüberliop, is A, B, C, D, E, F, G, etc. So it's fully alphabetic. The plug board at the back at the top, instead of the front at the bottom, is also alphabetic. And the lamp board, which you can't see so well, but that is also fully alphabetic. This machine is currently on display, as I said, at this museum in Hammersmith. It's a small museum. It's worth a visit if we ever manage to reopen again. And unfortunately, this machine is not going to be there much longer. I think it has about a year to stay there, and then it's moving to Warsaw. But we are working on putting in a holographic version to replace it. So I'm going to concentrate on a fairly small range of enigmas. There's just this convenient 5 on the list here. And this is a standard picture of it. Now, I'm just going to quickly run through Caesar Cipher, which leads into Enigma encryption. Supposing I want to encrypt a message, such as a very important message which must be kept secret. And if I just add 5 to every letter, so A plus 5 is F, B plus 5 is G, and so on. And then when we get to the end of the alphabet, Z plus 5 is E. So there's a wraparound modulo 26 to get to the values after we've got through Z in the encrypted characters. So a very important message which must be kept secret then encrypts to this text here, F, AJWD, NRUT, etc. You wouldn't normally leave the spaces in like that. So it's then broken up as shown on the bottom line to 5-letter groups. And then when decrypting, it's pretty trivial if you know it's a Caesar cipher, because you can just try a key value of 1, and if that doesn't work, a key value of 2, and if that doesn't work, 3, 4, until eventually you get to 5, and then you could just say, okay, take 5 off all the letters, and you end up with the original message. Now, there are other ways of cracking it rather than this brute force trying 1, trying 2, trying 3, and so on. And that is just to count the letters in the message. And if you know the language that the message is in, then you can fairly quickly determine what the key is. Now, the number of J's is much larger than the number of any other letter. And it is a well-known fact that in English, E is the most common letter used, except in certain publications where people have gone to absolute extremes to avoid ever using the letter E in the text anywhere. So you can just, given that the English letter frequency is ETION and so on, we can just pretty quickly say that J must be representing E and Y must be representing T. And J minus E and Y minus T both equal 5, which is the number I first thought of at the beginning of this segment. Now, if we want to make it a little more complex, we can start with a key of 5, but then for the second character, we'd use a key of 6, and for the third character, we'd use a key of 7. And that gives you the text that you see on the bottom line, GCMAI, and that has effectively flattened the distribution. So it's now not obvious what the most used character is. And you cannot work backwards. If you don't know what the algorithm is, you cannot work backwards to get the original plain text just by counting. So let's have a look at the major components of the Enigma. There's at the top in the back, there is this Zur Beachtung plate, which, as you can clearly see, is primarily cleaning instructions. It does have a few cryptological pieces of information and an important instruction that you should always close the flap on the front, otherwise you will end up with more lights coming on than you should get. Now, this is a little demonstration of how Enigma works. You'll see a set of rotors at the top. This one, the reflector, and this one, the entry drum, remain fixed. And then you have three rotors, the left, the middle, and the right. Below the rotors, you have a light panel. Below the light panel, you have a keyboard. Below the keyboard, you have the plug board, which is on the front of Enigma machines. So what happens? I'm going to press the letter A. So here goes the A key. And the first thing that happens, if you saw at the top, the rotors turn. The right rotor always turns. The middle rotor turns one step for every 26 steps of the right rotor, and the leftmost rotor turns for once in every 26 steps of the middle rotor. The algorithm is a little more complicated than that because of a hardware quirk, but basically you've got 26 possible positions of the three rotors, and therefore 26 times 26 times 26 possible starting positions. Current now starts to flow, and it flows into the plug board, which in this example happens to have the letter A plugged into the letter M. And then the current continues to flow into the rightmost rotor, the middle rotor, the leftmost rotor, to the reflector, and the current then reverses its path. And it's now come out of the rotor stack as the letter O. Now, as it happens in this demonstration, the letter O has been plugged to the letter H. So the end result is H lights up. Now, because the rotor's moved when I press the letter A, it means the next time I press the letter A, you are unlikely to get an H the next time round. There's a 1 in 26 chance you will, in fact, but it's unlikely. So the simple Caesar Cipher demonstration I was showing you shows that the actual shift that's being applied to each encrypted letter is changing with every letter. And this is a little Enigma simulation. And let's just show what's going on here. We started with the wheels positioned at A and A and A. And I encrypted the four letters AA. After I've done four letters AA, the wheels have moved on to AAE. The last letter was encrypted at AAE. The first letter would have been encrypted at AAB. Each rotor is in two parts. So there's a ring on the outside which is able to be rotated relative to the rest of the rotor, which is the actual thing that does the encryption. So this makes the encryption process somewhat more complicated. So, for example, here I've got an example of encrypting. This is a very long test message for turnover checking. And if I encrypted it with the wheel set at JFK and the rotors set for EWR, I was sitting in a hotel in New York when I first wrote this presentation, because as you probably know, JFK is John F. Kennedy Airport, New York, and EWR is Newark Liberty Airport, just over the border in New Jersey. Decrypting, setting the wheels back to JFK and leaving the wheels at EWR means I get exactly the same message back again when I decrypt. But if I now step on both the keys, the key setting, the wheel setting, and the ring setting, then you'll see that one of the letters is misdecrypted, the H in the box here. And if I step both of these items on by 2, then you end up with 2 incorrectly decrypted, and so on. So having the rings right as well as the key settings right is important. The wheels, depending on exactly which era of Enigma, are numbered in Roman traditionally. There will always in this machine be 3 wheels at any one time, and those 3 can be selected from 5 wheels in total or 8 wheels in total, depending on the actual timing of the system being used. The reflector, the rotor right at the left, can be one of A, B, and C. B is the most common. C was introduced later on. A was withdrawn fairly early. Now, the definition of the settings for the day is determined by a coding sheet. And here's an example of a coding sheet which I've created for February 2021. Today's date is the 28th, so we're looking at the topmost line of this coding sheet. And it shows that the Umkehrwalzer, or reflector, is the C reflector. The rotors being used in this case is number 1 in the left, number 3 in the middle, and number 2 on the right. The rings on those 3 rotors are 13, 12, and 18. The plug board is connected with A plugged into W, B plugged into F, C plugged into M, and so on. The Kenngruppen is not actually cryptologically significant. It's more used to identify messages which are being passed on networks, so recipients can tell if a given message is for them or for somebody else, and whether or not they therefore have to take it down and decrypt it, or if they can just ignore it and let it go by. So this is the front of the Enigma, the plug board, and with just a couple of wires plugged in. Now, if I happen to have B plugged into G and P plugged into Z, then the default decryption was BDZG, but we now have an encryption of GDPB. So having plug wires in drastically changes the encryption. There are 2 ways of attacking Enigma messages. In fact, messages from pretty much any encryption system. Firstly, there's the known plain text attack, where if you know the plain text or you are prepared to take a stab at what it might be, then you can develop systems to try and analyze and compare the cryptotext with the plain text. So one of the well-known features of Enigma is that no letter can encrypt to itself. So if you happen to have a message, and this is an example in English, whereas of course in the real world the examples would have been in German, nothing special to report, and you've got an encrypted version which is OPC, URL, VMM, and so on and so forth, then you can discount roughly half of the possible positions of nothing special to report relative to the encrypted message. You can discount all of those where, for example, in the first line, you can see the O in the word report is directly underneath the O of the line above, of the encrypted message line. But once you've thrown out the impossibles, you can then start to do some testing using, for example, the common example we show at the museum, the National Museum of Computing, is we have a plain text, an assumed plain text, a crib of Wettervorhersage, which is German for weather, and an encrypted message which starts off SNMKGGST. And you draw this rather nice diagram, which is called a menu, which I always feel looks a bit like an organic chemistry, some interesting molecule in organic chemistry. And you can then plug up the Turing-Welchman Bombe, of which this is a mock-up from a film. And I believe the lady standing to its left is also a mock-up from a film. And you can then run the Turing-Welchman Bombe to give you possible settings for the rings. At the back, you effectively wire in this molecular chemistry diagram, and you can then run the machine to tell you the ring settings. For 4-rotor machines, there are some machines were modified to have an extra set of rotors on the right-hand side, and the Americans had 4-rotor bombs for decrypting German naval messages, which also used 4-rotor Enigmas. Just a brief trot through other Enigma-like machines. This is the Lachida, a Polish cipher machine about which I gave a talk about 6 weeks ago, I think it was. There's a rather nice machine called a Fialka, Russian. It just means, the name just means violet, as in the flower. It's also called, incidentally, a fiołek in Polish. Instead of having 4 wheels, it has 10 wheels. Instead of having a plug board, it has a punched card, which is changed every day. It has an interesting keyboard because it can support up to 4 different characters on each key. So this one happens to be German and Polish and Russian. It has a connector on the side instead of the lamp board, and this connector can then be connected fairly directly to a transmitter. There's a Swiss machine rather similar to the Enigma called the Neue Maschine, which is rather an unoriginal name for a new machine. It has no plug board. It does have more rotors. In fact, each pair of rotors that you see there form one wheel. So it actually has the ring setting and the rotor position set into one pair of wheels. And then there's this machine, a Japanese machine, which I'm hoping to give a talk about maybe in May. And then there's the British machine, the Type X. The Type X is sufficiently similar to Enigma that it could be wired to simulate Enigma. Now we come to the harder stuff where you have no idea what the original message was. So you have no cribs to work with. And this is more the situation that the Poles had when they were trying to crack Enigma. Now, at that time, messages were sent using 2 keys. So there was a key for the day, which was 3 letters, and then a key for each message. And the technique was to encrypt the message key twice using the daily key. And that then gives you an interesting way into the system, because although you don't have a crib, what you do know is that Y and Z, in the example which I'm showing on the 3rd line, are encryptions of the same initial letter, and G and O are encryptions of the same plain text letter. And then one step on, W and O are encryptions of the same plain text letter. So you don't have a crib, but you still know that there are some interesting things going on with the pairs. An interesting feature is when you get pairs of letters which are in, how should I put this? We know that we are encrypting CAR twice. And when it becomes interesting is if one of the pairs of letters, the 1st or the 4th, the 2nd or the 5th, or the 3rd and the 6th in the encrypted version of CAR is also the same. And when this happens, it's known as a Sirmitsa. or translated roughly into English, it means a female. They are also called oculari, which translates as spectacles or eyeglasses, because when you're looking at an encrypted text, these females or oculari kind of look out of the page at you. So you have 3 kinds of samitsa: a 1,4 samitsa, a 2,5, or a 3,6. Now, various methodologies were created to take advantage of these. There's a well-known thing called a płachta Zygalskiego, or the Zygalski sheet. Marian Rejewski, who was one of the foremost crackers of Enigma, did comment somewhat dryly that this, of course, is the translation. When these sheets, the Zygalski sheets, were superposed and moved in the proper sequence and in the proper manner with respect to each other in accordance with a strictly defined program, the number of visible apertures gradually decreased. And if a sufficient quantity of data was available, there remained a single aperture, probably corresponding to the right case. That is, the solution. Now, you might think that's not a great advertisement for this system. But, and in fact, I tried to create some Zygalski sheets, and I tried to make them work. And I can tell you it was extremely difficult. And trying to make this work, in the end, I had to give up. But of course, unlike in the 1930s and the 1940s, we have computers. So I was able to invent a system which generates Zygalski sheets and then places the one on top of the other. And I can, in fact, prove that the Zygalski sheets worked. That, however, will be the subject of a whole other lecture. There's also created by a gentleman called Jerzy Rzyckiego, who was also working with Marian Rejewski and Henryk Zygalski, called the Metoda Zegara, or Jerzy Rzycki's clock method, which was a statistical method of comparing 2 encrypted messages, given that you know what the starting position of one, to determine if the second message could have had a close start position, or indeed to determine if the second message was even using the same wheels. And this was subsequently, independently or otherwise, reinvented as Banburismus. Another machine that was created during that era was a device called the cyclometer Mariana Rejewskiego. And once again, I show this picture with permission of Marek Grajek, a colleague of mine. And as it happens, I have one of those as well, which I've created, but that is also the subject of a whole other lecture. But let's get back to the Bomba, the eponymous device of this talk. Let's say now we're going to not have an initial key, the daily key. We're going to have an initial key which changes for every message. And then we're going to have a second key which changes for every message if it's being used correctly. So we'll have an initial key for this message, which I've denoted as KYI, and a key for the message, which I've denoted as KYM. So once again, we're encrypting KYM twice using KYI, and then we preface the message. Then we encrypt the message using KYM. And then we transmit KYI so that the recipient knows what the initial key was. And the recipient then knows what the encrypted version of the message key was. And then the actual message follows in fully encrypted form. Now, you might think this gives away the game because you've actually told the recipient what the initial key was that started off the sequence. But what you haven't told the recipient is what the ring settings were. So we only know the positions of the 3 wheels. We don't know the ring settings. We don't know which wheels are actually installed on this day. We don't know in which order the 3 rotors are installed. And we don't know what the plug board connections were. We only know those things if we are the recipient and we have a copy of the coding sheet which the transmitting machine was set up for. Once again, the coding sheet. So it's identical at the receiving end to at the sending end. But you can do magical things with these samizze or oculare, because I've shown you that one before. Just a reminder of how the samizze are categorized. The number of positions that rotors can take is 17,576. That's the number of possible start positions. 26 times 26 times 26. The possibility of having a female at a given position is just 1/26th of that. And the possibility that there could be 3 females at given settings is very, very much smaller. And in fact, I kind of liken it to this spectroscopic image, where if you are looking at these patterns of pairs or patterns of, I think these are like spectral responses, then given if you've got the one at the bottom, then you can fairly easily work out which row this came from, leaving aside the fact of the colors. Another way I like to look at it is fingerprinting. As if anybody who's ever watched CSI or NCIS or any of those things, they can always work out who the perp was just by looking at a partial fingerprint. So although they might not have this full fingerprint at their disposal, they might just have a bit up here and a bit down here and a bit down here and a bit down there. And they could say, oh yes, we know who committed this crime. So if we have a number of intercepts on a given day, and we have some females to look at. So for example, the first 9 characters of a transmitted message was TSG JCS QCQ. And we have a C here and a C here, and that's going to be at position not TSG, but TSH, because it's 1 position further on. Similarly, we have a J here and a J here, which is 2 positions further on from the CCI, which is CCK. And here we have VUK, and we have the E as the first character, so we know the actual setting was at VUK. Then we take our Bomba and we start to install wheels on it. Now, we don't actually know which wheels to install, so you have to have multiple Bomba. Bombe, by the way, is plural of Bomba, so you have to have multiple Bombe. And you would stick for a given rotor set, TSH and TSK, 3 wheels on set to TSH and 3 wheels on set to TSK. And then we'd have VUK and VUN and ETK and ETN. And you have to have 1 Bomba for each possible order of the wheels. So you'd have to have 1 which you would set to 1, 2, 3. You'd have 1 that you'd set to 1, 3, 2, and so on. So you need 6 Bomba to do the full program. Let's have a little bit of a detour. This gentleman is Marian Rejewski, who's considered to be the foremost of the code breakers. It proudly says "Skrakowałem Enigmę." I'm told that "Skrakowałem" is not really a real Polish word, but it's easily translatable to "I cracked." The little text down bottom left tells you that it was a Polish mathematician and cryptologist in the year 1932 broke the German machine cipher Enigma, along with his colleagues Henryk Zygalski and Jerzy Różycki. Unfortunately, this picture seems to have been taken in front of a colossus, but that's okay. This is kind of his fan club that we're looking at, a website for his fan club. And I guess they could use Colossus, even though he had nothing to do with Colossus. A lot of the work they did in Poznań, which is a city in Germany, in Poland, excuse me, in between the German city of Berlin and the Polish capital, Warsaw. And there's a train line that runs from Berlin to Warsaw, and it happens to stop at Poznań. In Poznań, they have this memorial to Marian Rejewski, Jerzy Rosicki, and Henryk Zygalski, which is outside the Poznański Zamek, the Poznań Castle. A number of us have been puzzling about what all these numbers mean, and the only thing we know, the only thing we've managed to work out is that we know that Henryk Zygalski was born on the 15th of July 1908, and he died on the 30th of August 1978. As it happens, Henryk Zygalski stayed in Britain after the war, and he's now buried in Chichester. But that's not particularly relevant to this story. And I'm just showing you one vacation photograph, not because you really want to see me, but I'm just pointing out that behind me and behind the, just beyond this memorial, is an Enigma Museum, or will be an Enigma Museum, Enigma Adventure Center, Enigma Experience Center. It's called a lot of things. I've been told not to call it a museum by one of the people working on it. It'll be opening in fairly soon now. Of course, it's been delayed by various problems that we won't talk about right now. This is a more modern version of the text, which you can work from to discover how this the Bomba works. Notice the magic number 17576, positions of the rotors. Now let's get on with my presentation, my version of this machine. This, as you can see, sort of resembles the box on the left. There's 26 switches in 3 vertical columns. There's a big switch, which is the power on-off button. So I've got 3 rows of 26 switches. And instead of having the rotors on top, I'm simulating them in software. And the display on top, the point-of-sale display on top, represents the positions of the rotors and various data concerning them. So the hardware design, so the hardware is a computer, primarily with a point-of-sale retail display here. Oops. Some USB ports with interfaces to the rows, the columns of switches, and some LEDs, light emitting diodes. So I've now simulated this. Of course, a computer is no good without some software. And this is the flowchart of my software. I don't propose to go into these diagrams in too much depth unless anybody really wants to know about it. But basically, I've taken the functionality of the Bomba as it's been documented in various publications, written it in software, and I'm running it on the laptop computer that drives the lights and the switches. So I'll just skip this. This is more for serious programmers. And the output's on a display. And also I ring a bell because I can. Not a real bell, but I play a bell sound. Now, what can you do with this information? When you find 3 females at the same displacements from each other, you can then do a bit of math that says that to the first approximation, wheel setting A plus ring setting A is approximately equal to wheel setting B plus ring setting B. And that goes through the sequence to wheel setting Z plus ring setting Z. So the results of setting the wheels in any of these positions with their rings, you end up with approximately the same encryption. And I showed you this already. You can see there's approximately the same encryption, although it gets a bit flaky in the middle where the differences are. So if a given text is sent with wheel settings UVW and the rings on those wheels is X, Y, and Z, then if we can find a place where the rings and the wheels give females, then if we find a matching point with rings with wheel settings RST and we assume ring settings AAA, then we know that UVW plus XYZ equals RST plus AAA, where AAA is traditionally going to be 1. So we can then do a bit of math that tells us what the ring settings were in the first place. X comma Y comma Z is equal to the position of the female R plus S plus T plus the 3 default ring settings minus the UVW wheel setting. And this is quite similar to the operation of the Turing-Welchman bomb, where they assume that the rings are at where the rotors start at ZZZ, and it then works out the ring settings based on that. So all we have to do is calculate RST minus UVW to get XYZ, which is the ring settings, when the message was sent. Somebody's just asked me what language software, and the answer is Visual Studio 6 C++. And then we repeat for, we obviously need to have 3 females at a particular given relative position to each other. So we obtain X prime, Y prime, and Z prime, and X prime, X double prime, Y double prime, Z double prime. You're welcome. And they should all be equal. The displacements of the ring settings should be equal to the displacements of the initial message key text. So then I need to test it, and then I've gone back to the old school flowchart, and I just generate a huge file of every possible setting, encrypting every possible combination of letters from AAA to ZZZ. And once again, I'm not going to go into this too much, except for programmers who might wish to ask me later. And now we have a little demo which shows my Bomba rebuild functioning. Now, I don't know if you're going to get sound effects or not, but I'll just speak over them anyway. So the camera was at a slight angle, unfortunately, but still. First of all, I'm going to set the wheels to 3 initial keys. So I actually chose some initial key positions which are fairly close to each other, so I only have to set 1 letter on each. So I've thus far got ABP, QBP, and HBP. And you'll see on the bottom row, there's each of those values plus 3. And I then determined that I was getting females with values of Y, R, and Y, which you can just see appearing on the top, Sumitsa : YRY. And then I start the machine running. And it just steps through the wheels, steps the rotors, and I've chosen a fairly fast example here. Bell rings, and it stopped with the wheels positioned at CET, SET, JET. Now, as I intimated earlier, I don't really need that box. The whole experiment runs on my laptop, but people like a bit of a show. So let's just show what's going on the actual laptop screen this time, rather than on the switch box. First of all, I start with the wheels at the default position, which is 3 rows, AAA and AAD. So AAD is 3 on from AAA. So I've got 3 sets of wheels. As it happens, I'm using 1, 2, and 3, left, middle, right. Then I actually set them to those start positions. So at ABP and ABS, I have a female of Y. At QBP and QBS, I have a female of R. And at HBP and HBS, I have a female of Y. This little text here is a comment from a text file that I loaded these settings from, so it doesn't know the answer yet. I then run the software, and approximately 15 seconds later, it stops at CET, SET, and JET, and I subtract the original ABP, QBP, and HBP to get the values Y, X, and W, which were the actual ring settings that were being used at the time of the initial encryption. This is a log file from my software, and it shows that CET, SET, JET, and then CEW, SEW, JEW, wheel settings 1, 2, and 3, and that there are the YRY females were originated as ATE, ATE. So that's a good result. Of course, I created this data knowing what the results were going to be, because that's the way to test the software. I then started it running again, and it then ran for about a quarter of an hour, and it didn't stop again until the wheels 2, 3, 1 were in position. This system of mine starts at 1, 2, 3 and does every possible rotor order, selecting 3 out of the 3 rotors 1, 2, 3. So it goes 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and so on. So it's a fairly foolproof thing. It doesn't have, in this case, there was only two false stops. There's this one, and then a subsequent one when 3 is in the leftmost position. Now, there are cases when the Bomba does not work. And what are they? Case 1 is for turnovers. And if while the female was the 6 characters of the message, the second message key happens to be a turnover, then that is an unrecoverable problem from which you can't get out, of. In other places in the message, then you may or may not get a good answer. But what I discovered was that you got wrong, but still usable solutions. So in this case, I did some encryption using ring settings of BPT. And I've played around with having turnovers in various places, which means that in some cases I got a response of BQT out of the Bomba. So it's workable, but you have to know that actually it might be 1 out, either up or down. And another test resulted in CQT. So not only is it 1 up or 1 down on the middle rotor, but it could also be 1 up or 1 down on the leftmost rotor. And you basically get partial females or partial stops, where you have to do a bit of analysis to try and get the original message back. Now, another case is when the Steckerbrett is involved, or the plug board. And if any of the characters involved in the second message key are changed by the plug board, either on the way in or on the way out, then you have a problem. You aren't going to get a workable solution. So you've got maybe a one in, you're only dependent on 4 characters not going through the plug board, which is 3 characters of the original message key or the 1 character coming out. And if those 4 characters don't go through the plug board, then you have a good chance. Now, it would be interesting if we could find an operations manual for the Bomba, but in fact, there isn't one. No such thing exists. So I just produced my own sort of manual, which says you encrypt some messages, you normalize the headers to get pointers to the actual females, and then you enter the process with ring settings from stop. You set an Enigma with the ring settings, you process a message. If you get a good decryption, then you're done. If you're not, you have to try again. And one of the trying agains is to add plus or minus 1 to each of the ring setting positions to see if you can get a good message. So covering that condition where you've got some turnovers in awkward places. Now, another interesting piece of research that I decided would be fun to play with was whether or not you could wire a Turing-Welchman Bombe to act as a Bomba Polska. So in other words, can you create a menu for 3 females? And I had a go at this, and I determined that you could, but what you end up with is 3 separate menus. And the Bomba can only cope with 2 separate menus. It can't run three rows of separate menus. And that assumes that I was using 3 different females. So I had a female which encrypted to D, a female which encrypted to M, and a female which encrypted to V, which gave 3 independent menus. But then I tried again with 3 females the same. So if I encrypted some messages, some test messages such that I only looked at the females which were W, or any other letter of the alphabet would do as long as they were all the same, then I can create a menu which looks like this. And I can then, and that's the Bomba result with 3 sets of wheels and the WWW females, and I can churn it around and can get YXW as the ring settings. I then plug it up onto a Bombe, Turing-Welchman Bombe simulator. And in fact, indeed, I wish I could see what I got, but it's, the top shows an X, the middle one shows a W, and the bottom one shows a V. And it shows that the female was a W. And wait, you're probably saying, XWV is not the same as YXW, but in fact it is, because the wheels on a Turing-Welchman Bombe are 1 step out relative to a real Enigma rotors. And in my Bomba reconstruction, I've assumed real Enigma rotors, not shifted Enigma rotors such as the Bomba uses. So there was a large number of these Bombe which were created, and the question then arises, where are they? Gdzie są Bomby dziś? Where are the Bombe today? Now, when the Poles were evacuating Poland as their country was being invaded, they were getting out of Warsaw and they were escaping. And this is an escape route which was drawn by one of their commanding officers, a gentleman called Guido Langer. And I'd like to thank the Institute Józefa Piłsudskiego for this map. And it shows that on 6th September in the evening, they left Warsaw. They, Piry to be exact, and they escaped east and south, eventually arriving at this this place here, Wusk. That's L with a bar, U-C-K, Wusk. They then took a little detour to the left to Uchiwug, where, as told by Dermot Turing in his book, The Real Story of How Enigma Was Broken, also available in Polish, Prawdziwa Historia Złamania Szyfru Enigma, also available in French. All of the machines they brought with them were burned and or destroyed. So there are people who are interested in trying to find these machines. Now, you may recall I mentioned a place called Wusk, which is spelled in English or spelled in Roman as L with a bar U-C-K, which you'll see now it's got a Cyrillic name and it's been retransliterated in English into Usk. And that's because all of this area is now in Ukraine. And Ustiwug, or Ustiwug, is also in Ukraine. So I'm sure there are people who would be very interested to go into Ukraine and dig big holes in a field somewhere, but at the moment this hasn't happened. So, burned and buried. Further reading, there's this rather fine book by Marian Jurewski, Wspomnienie z mej pracy w Biuro Szyfrów, which you'll be pleased to know you just turn over and open from the other end and it's all in English. There is also an article in Cryptologia, and that completes my lecture. Thank you for your attention. And I'd be happy to take questions.
Hi, Jerry. It's Martin.
Hello, Martin.
Hi there. If the Germans had carried on using that format of encrypting,
yes,
do you think it would have been possible for them to use the Bomba on a four-wheel system? Would they be able to expand it to do that?
Oh, you mean having four-letter keys instead of three-letter keys, and then adding yes, I guess. Then putting four rotors on top of the Bomba. Yes, I think that would continue to work.
Yeah.
But as it happens, they didn't. The Marianne book, where is it available? You'll find it on Amazon. It's this book here. Oops, it's not going to show, is it? Yeah, there you go. Marian Jurewski, Wspomnienie z mej pracy, and then you turn it over, and then it says, whoops. Oh, come on. Well, trust me, it's in English on the other side. Yes, now it says memories of my work, but you can find it on Amazon or eBay for that matter. Not a lot of copies of them were made, as far as I know, but I've certainly got a couple of copies from Amazon.
Question for Martin: when are you going to start on a Bomba?
That's a good question. I'll have to try and understand this first. I think you've blown my brain trying to. There's lots of functions. I'll have to have a look at what you're doing, Jerry. You have to send me your code so I can run through it.
You're welcome to look at my code.
See if we can work it out. Maybe that's the next one.
I can certainly send you the flowcharts.
Yes, I'd like to see it.
Flowcharts, yes.
Yeah. You know where I am. Yeah, I'd have a go and see if I can work it out. Yeah.
So I do see that there are two representatives of the, or maybe only one representative of the Institute Józefa Piłsudskiego. Maybe Roman dropped out. Oh no, Roman is there. My mistake. Roman and Anya. Witamy.
Yeah, thank you very much, Jerry, for mentioning us so many times. And I hope we can just repeat your lecture again on our website or our social media. It's really interesting, and you add some new things to your lecture. So yeah, we're looking forward to have you again.
Well, yeah.
And your Polish is really great, and how you pronunciate all these names is really brilliant. Congratulations.
No, dziękuję bardzo.
He practices on us quite a lot.
Oh, poor you.
Yes, poor you indeed.
Yes, and I would just add, you mentioned that we're working on the holographic version, for which we, thanks to your technical advice.
Yes.
And the software and let's say the simulation is all but completed in the next couple of weeks or so weeks, but we've got the hardware to do yet. And possibly about 3 months' time, it might be available. But but we're looking for a good display area for it. Of course, we want the main Enigma, the Polish Enigma machine, to remain where it is whilst we've got it, and then we'll substitute it in the future. So everybody, as Jerry's mentioned, is welcome to come along and have a look when we are open to see the actual machine and the holographic version at some point in the future. Thank you for your wonderful presentation.
Proszę bardzo.
Dziękuję.
Kto pytania? Anybody got any questions? Or are we done? Well, you're welcome, Martin. And Chris. Okay, well, I guess I'll close the call at this point, unless there's...
My brain's completely scrambled. Thank you very much.
You're welcome. We'll just put your brain on my Bomba and it will unscramble it, perhaps. Okay, well, thanks everybody for attending.
Thank you.
You're welcome.
Thanks, Jerry. Very good.
Please keep looking at our calendar. We have more talks coming up. Well, thank you very much.
Yes. Thank you, Jerry.
Thank you, Jerry. Thank you.
Okay, goodbye.
Thank you.
Yes.
Do widzenia. Do zobaczenia. Bye.
Do widzenia.
Do widzenia. Dziękujemy. Thank you.